Today we will look at the effect of electrolytes and non-electrolytes on the freezing point of water. Sodium chloride will be our electrolyte and urea our non-electrolyte. As you may remember, an electrolyte forms ions in solution and a non-electrolyte does not. Generally, electrolytes are ionic compounds and non-electrolytes are molecular compounds. There are exceptions, of course, which you learn about in other parts of the course.
Hi, today we're going to be measuring freezing points, and we are going to be measuring freezing point of pure water. We're going to put a couple of different solutes in the water and make solutions and measure their freezing points. We're going to do a little bit of investigation of whether adding this particular solute has an effect on the freezing point. So the first thing we're going to do is, in order to freeze something, we need to have water. We're going to start with pure water in here. So I'm going to measure out 25, it's a conveniently graduated cylinder, about 25 milliliters of water. Okay, that looks pretty good to me. I'm going to put a stirring bar in there.
So I'm going to get the computer set up. So I'm going to go over here and click on this weird looking pyramidal icon called the capstone icon. It's opening up the software. And I'm going to choose one of these types of displays. I'm going to click on select measurement. And oh, I haven't paired the device yet. I have to go to hardware setup. And I have to turn on my temperature probe, and it recognizes it right away. And I just click on this. Okay. And I think that's all I have to do. Select measurement. Now I can select, now temperature is one of the choices. So when I hit the record button, it'll record a temperature. On the graph, click select measurement. I'm going to do that again. Again, I'm going to choose temperature, just like I did before. And then I'm going to hit the record button. Now, as you saw us do, Mrs. Syak already put the 25 milliliters of pure distilled water in there, and then we put a stopper on it. And we're going to take the temperature probe and put it inside. All right, so we're going to put this in here. So you can look at the temperature, and it's recording 24.5 degrees right now. Temperature is about 24.4. It's going down there. It's pretty much constant. I'm going to move this.
Let's put it on the stir and see what it does.
Oh yeah, let's do that. Okay, so we're going to go over here. By stirring it, we'll have it come to temperature equilibrium, more quickly. What we're going to do next is to prepare an ice salt bath.
We need to build an ice bath around the water. So what we're going to do is measure out a little sodium chloride here. Now you all know, if you've ever made ice cream, that you've got to lower the temperature of the ice.
So as Mrs. Syak was telling you earlier, the temperature of an ice salt bath is lower than the temperature of regular water ice. And that's what people use to make ice cream, right? Because it freezes the ice cream much better, and it has better texture when you do that. So I think what we're seeing here is that we've pretty much reached a constant temperature of 24.0. It might change by a tenth or so, but this is looking pretty good. So I think we're okay to do build the ice salt bath around it.
Okay, so what I'm doing now is building an ice bath around the apparatus. And so I put the apparatus, our graduated cylinder, into a large beaker, and I am going to fill it with a little ice and a little salt and a little water as well. Now the water also comes from the melting part, so I don't want to add too much water. Wow, this is getting frozen in place. I would like to go. Alright, so I'm going to put a little water in here. We don't have to fill it up to the tippy top because our water is down near the bottom of the cylinder. So let's see what's happening to the temperature as we do this. And I may have to replace some of this as we go along. I think that'll be okay for now. So what happens is this mixture of ice and salt and water will all come to an equilibrium temperature. So let's see what happens.
You can clearly see that the temperature is starting to drop.
So the nice thing about this whole setup is that we have a real nice picture of what's going on, as well as the data about each particular temperature. And it's very satisfying to see that go on. So let's see what happens.
As you can see, the temperature has continued to fall. I've changed the axis, so now you could see it's going from 20 to -20 on the y-axis. And the x-axis is just the time that's passed in seconds. So we're at 600 seconds. That's about 10 minutes. Is that 10 minutes already? Wow. Time flies when you're having fun in the lab. And from time to time, Mrs. Syak replenishes the salt ice bath to keep track of it. And the temperature continues to drop and is now at 10.6 degrees C. And the temperature is now 8.4 and dropping, 8.3. And the bath
Kind of makes you want lemonade, this bath, you know. It's a nice little slushy thing.
I don't know. For me, it's ice cream I want.
Oh, ice cream.
Maybe we'll stop at the Newport Creamery when this is over. What do you think? Anybody know what the freezing point of water is? Go ahead.
Wow, it's still going down. Gee. So, have you looked up the freezing point of water? You should know what it is. You know it's 32 degrees Fahrenheit. Celsius? What is it in Celsius?
Okay. Well, what's going on here? We're at 1.8 degrees. 1.7. Make sure you can see that's 0 down there. What does it look like this curve is doing? Look at this. Now it's negative 0.2.
Oh, went up there for a minute.
Oh, yeah?
Yeah. Went down again.
Huh, look at that. It's dipped below the zero. Well, we're going to see what happens to this curve.
Pretty cold.
Temperature is now negative 3.3. Mrs. Syox says it looks like it's still liquid in here. There is a phenomenon known as supercooling, which we may be seeing right now.
Oh my gosh.
Look at that. So it was going below what we know to be the freezing point, and now it's jumped back up. It was super cooled liquid, and now look. Let's get the whole picture here. You can get the big picture here.
There you go.
I was just trying to get it a little better. Okay, so now we have the big picture. You can see we started out with room temperature, about 24 degrees. The temperature dropped very gradually. We thought it was going to approach zero nicely, but instead it became super cooled. It went below zero, because this black line is the zero, and then it jumped back up to the freezing point.
And while the freezing is actually occurring, we have a little bit of liquid, a little bit of ice. And until all that liquid turns to ice, it's going to stay at this temperature. And that's why it's so great for your lemonade.
And you could see that the temperature is constant, and it will remain constant until all the liquid, like Mrs. Syox said, is converted to ice. Now, what's the temperature of the bath at this point?
Oh, let's see.
So if we take a thermometer and just record the bath temperature itself.
All right, let's see.
Okay.
Well, it's going down. It's not zero. Let's see if you can see that.
Oh, it's way down there. That's negative 10, almost. Negative 8, maybe?
Yeah,
So
negative
it's
8
below
degrees.
zero. You could see that's the temperature of the bath. So the question is, you know, why this graduated cylinder is sitting in that bath? Why isn't it at the temperature of the bath? It's been sitting there a long time. But what has to happen first is that all of this, while it's going along this line at zero, water liquid is being converted to ice. If it were to convert all the way to ice, then the temperature of that ice would drop. But right now, all that's happening is the phase transition from liquid to solid is happening. Okay, so what I did was make a little box here, which has selected those points, and over on the left, it's telling you what the average temperature is, the mean, and indeed it was 0.0, which is telling us that our thermometer is indeed nicely calibrated.
Okay.
Hi. So I'm going to tare this beaker, and then I'm going to add about 1 gram of urea, which I actually pre-weighed, so I know that this is about 1 gram of urea. And indeed, it is 1.001 grams. And now what I've also done is I have measured out about, well, pretty precisely, actually, I think it is another drop, 25.0 approximately milliliters of distilled water But I'm going to weigh it. I'm going to pour it in here. I'm making a solution of urea in water. And you can see the mass there, 25.969 grams. All right, my solution. So I've been swirling this urea for a little while, but urea is very soluble in water. So you can see there's maybe one little crystal left, so I'm going to do a little more swirling.
Put it against the dark background. Yeah.
It's dissolved.
So now we're going to do the experiment over again, but we're going to use the urea that Professor Cooley just measured out. So we have a really nice solution of urea. We've measured everything about it, so we know how much it weighs and we know how much urea is in here. So I'm going to repeat this experiment. Okay, and now we're going to put our probe in this mixture. All right, and we are going to build a bath around it, but first we're going to start the temperature collection to see what our original temperature collection is. So it should be at room temperature, pretty much.
Looks like it's at 24.4.
So I'm going to let that run for a few minutes, and I'm going to build the bath just like I did before. So let's let that go, and I will build the bath as I go along here.
So we're recording the temperature, and Mrs. Sayak is building the bath.
All right, the temperature is coming down a little bit, 21. It's got a long way to go. This is the urea experiment. In the urea experiment, the temperature is now 15 and dropping rapidly. I've measured the temperature of the bath. Looks like it's below negative 10 degrees C. We're at 13.6 and dropping.
It's falling fast, and the temperature is 11 degrees now. The temperature is now 7.5 degrees. It's still dropping. In the urea experiment, the temperature is now 0.8. It's not below zero yet. You can see the horizontal black line is the zero, so it's getting there.
And here the the urea solution, the temperature has dipped below zero. It's at negative 1.6 now and dropping.
We're down to negative 3.3 in the urea experiment. Still dropping slowly. Now we're at negative 5.3 on the urea experiment. It's still dropping. The urea experiment, big things are happening here. The temperature has gone back up. This was a super cooled solution, and now it's going to come back, and we'll be able to find the freezing point by extrapolating the points that it levels off to back to the mixing time. I mean, back to the, well, we'll show you.
So as you see, what I've done here is I've taken the points in this box, extrapolated them back, fitted them to a line, extrapolated them back to the freezing point curve, and found that point right there where that extrapolated line intersects the freezing curve. And it looks like I have
a negative 1.5 degrees C as the freezing point of this urea solution. Okay, so here is a closer up job. I expanded the scale so we could do this a little more precisely. And I extrapolated that line back. This is a close-up of it. And it looks like it's more like 1.4 degrees C. I'm going to go with that because this was done with a nice close-up. This is, again, the urea experiment.
So this is just a summary of the data for the urea run that we just completed. It gives the mass of urea that was measured, the mass of the urea plus water, and then it gives the freezing point of the solution. This experiment was repeated for 2 other masses of urea, and you can see those masses are given here. And also the masses of the urea plus water for each of those runs are given here, and the freezing points that correspond to those runs. And what's shown next is the progress of this experiment. It started at room temperature, approximately 24 or so degrees C, and now it's gone down considerably where we pick up the video.
.1 and dropping. 12.9 keeps going down. And now we're at 6.2 and dropping. 3.5 degrees C, it's still going down. That's down to 1.2 degrees C, but it's still dropping.
Showing you this for a while so you could see how long and boring it was for us to actually do this experiment. So maybe you should be glad we're not doing it in the lab. Showing you this for a while so you could see how long and boring it was for us to actually do this experiment. So maybe you should be glad we're not doing it in the lab.
Negative 5.3, all right. Victory!
Whoa! I missed it, huh?
Well, I missed it too.
Oh, thank you. Thank you.
We're so happy. It's super cool.
Thank
and now
you.
it's coming back up to what the freezing point's going to be.
And what is it?
And I hope that the computer doesn't reboot, because this is where we were when it rebooted last time. And here is the NaCl. And we're getting some leveling off. We may actually be able to get the result from spreading this out a little bit along the x-axis.
What is it? Oh.
So we took the horizontal portion, almost horizontal portion of this curve, extrapolated it back to the freezing point curve, and then we put a coordinate crosshairs on there and found that the temperature of the freezing point is negative 2.1 degrees C. This is standard procedure, believe it or not, for finding a freezing point. And this is the sodium chloride experiment.
So here's the data for the run that you were just shown. It gives the mass of the sodium chloride, the mass of the solution, and it gives the freezing point that was measured on the graph, which is negative 2.1 degrees C. Here is shown data for 2 additional runs that were done with different values of the mass of sodium chloride. So here is the data for those 2 different masses for those solutions, and also the total mass of each solution, as well as the freezing point of each one of those solutions. This we call run 2 and run 3 for NaCl.